Hello, what I want to talk to you about today is problem number 2 from the quiz. So that was the pKa problem and the Wittig reagent. And so I have the phosphonium salt that we started with. And so let's just work through the problem and see how I wanted you to think about this. So the first one says draw the structure of the conjugate base. Right? And so we're going to lose a proton, and hopefully it's clear that that's the position where we're going to lose the proton from, right? So we're going to end up making the phosphonium ylide is what it's called, and that's the Wittig reagent. So it still has one proton, right? And so there's our acid going to the conjugate base, okay? And so this is the conjugate base that I wanted you to write at the answer to part A. And again, I kept the ethyl group listed as just ET, so you would focus on the protons there and you'd lose that proton. Right? And so the second question was, what's the pKa value for this acid? And once we got you looking in the right place, I was hoping when you looked at the Bordwell pKa table that you'd figure out the pKa for this one. And if you looked in the table, the way that it was listed was, it was listed like that, and then there were a bunch of things that X were equal to. And the key thing was recognizing that if you look at X, X is this group right here, and if you figure out what the molecular formula for that group is, it's CO2 ethyl. And if you look up where X equals CO2 ethyl, then you find the pK for this, and the pK for this thing is equal to 8.5. All right, and then the question says, how does this compare to the acidity of other CH bonds? And why this molecule have a different pKa? And that's when I was hoping that you would focus on the structure of the conjugate base, because again, when we try to explain pKa values, we look at the structure of the conjugate base. And if you look at this conjugate base, you'll notice that you can draw a resonance structure that we're pretty comfortable drawing, where we delocalize that charge onto the carbonyl oxygen. Right? And the other thing that some of you noticed, which is a really important point, is that you can also draw a really interesting resonance structure where you move those electrons toward the phosphorus, and then you get an expanded octet on phosphorus, which is pretty interesting, right? And then you end up with something that looks like this, in which you have no formal charges, right? So that's a pretty stable resonance structure. And if you looked up what the Wittig reagent is in your book or online, most times people will write the Wittig reagent in this form because it's the most stable resonance structure. Right? So what I was hoping for your explanation for part B was to say, look, there are these 3 resonance structures and one that's really stable, and so that helps us explain why this is such an acidic proton, because you end up forming, make sure we have that, you end up forming a stable conjugate base. Okay? All right. So then going to part C, it was, let's find a base that's going to react with this phosphonium salt to give us the equilibrium constant that we want. And so this is where, to me, this problem got a little bit more challenging, because now you have to think about what's going on in terms of an acid-base reaction. All right? And so this is what I wanted you to think about. I wanted you to think about, here's the reaction that we're going to run. All right? So we're going to have our acid. All right, we want to react that with a base, and it's going to be some sort of base that is negatively charged, and there's going to be some equilibrium where we're going to form the Wittig reagent, which is going to be the conjugate base plus a conjugate acid. All right, and our negatively charged base is going to give a neutral conjugate acid. Right? And we know that we have pKa equal to 8.5 here. And now the key thing is that we need to find the pKa of a conjugate acid, right? And how do we know what pKa we're looking for? We want the difference in these pKa's to be 10 to 15, right? Because I said I want the equilibrium constant between 10 to the 15th and 10 to the 10th, all right? And so what we want is the difference in pKa's to equal somewhere between 10 to 15, all right? And so I hope that you then recognize we're going to look for a pKa that's somewhere here between 18.5 and 23.5, right? If we have a pKa in that range, we're going to favor formation of the weaker acid, and the equilibrium constant is going to be 10 raised to the difference between these pKa's, and that will give us the correct equilibrium constant. All right, so we're looking for a conjugate acid out here with this pKa value. And a lot of you said, oh, if we look at the table, we find acetone has a pKa equal to around 20. I think some of you found that it was 19.2. Let's just call it 19.5 so it's easy to do the math, right? So if that's 19.5, right, remember what that's saying is that we're doing the same equation as we have up top, right? And that's going to give us that conjugate base, right? And so when we're looking at putting it into this equation, right, this is going to be the base up there, all right, and this is going to be the conjugate acid, all right? So the base moves up there, conjugate acid goes over there, all right? So that's a really important point about what's going on in this reaction. Okay, so let's draw out what the final reaction looks like. So we're going to have our acid and base, right, and we're going to form a bond between the hydrogen and the negatively charged carbon on the base. So those electrons are going to go to form that bond. The electrons in the CH bond are going to stay behind to form the Wittig reagent, right, and give us the conjugate base. And just to highlight, that's the new bond that we've formed, right? So we now have made acetone, right? And again, we have our acid plus base going to the conjugate base and the conjugate acid. Again, the pKa values have are in the correct order, so that when we think about the pKa difference, it's going to be 19.5 minus 8.5, which equals 11. So that gives us an equilibrium constant of 10 to the 11th, favoring the products because we have the weaker acid here, the stronger acid here. All right? And one thing to be clear about, there was some confusion where some of you said, oh, if we have the pKa of acetone, we're going to use acetone as the base. And you said that you wanted to make this bond because you correctly identified oxygen as the most basic atom in acetone. But this is definitely not a reaction that's going to be favored, right? So that's the reaction that you said. Again, let's keep this separate. And you said that you're going to make the Wittig reagent plus protonated acetone. And again, the key thing to remember is that this molecule is now the acid, and you need a pKa for this. The pKa for this is going to be somewhere around 0. That's a very strong acid. So if you run this reaction, the equilibrium favors the reactants, and you're not going to get what you want to happen. Right? So that's the key thing in the take-home message from this problem, is to recognize when you're doing these sort of acid-base pairs that you need to think about it in the correct way, where you take the acid And then the other acid is the conjugate acid, right? You don't react an acid with an acid. It's an acid with a base, and then conjugate acid, conjugate base. And so that's a really important point to think about. And we can definitely talk more about this in office hours with the tutors, Q&A sessions, those sorts of things. But I think that was the key take-home message. Make sure you're thinking about this equation, all right, so that when you find the conjugate acid, you put it in the right spot, and then the pKa values work out. All right, so again, I think that's everything that you needed to know for problem number 2. And again, happy to talk about this more in person.